Okay, welcome back to another video on the Maths channel. It's your teacher, Mr. Lim here, and in this video we're going to be looking at similar triangles. So by the end of this lesson, you'll be able to identify whether two triangles are similar or not using the four tests, formally prove that two triangles are similar, and solve problems involving similar triangles. So let's have a look at the first part of this lesson, the four tests that identify similar triangles. Two triangles are similar if they have the same shape but are different in size. This means that they'll look exactly the same except one of the triangles is a larger version of the other. Therefore, in similar triangles, all corresponding angles will be equal and all corresponding side lengths will be in the same ratio. So they'll have the same scale factor. The four tests to prove similarity are very similar to the four tests to prove congruence. The first one is two pairs of corresponding angles are equal. We like to use AA or equiangular when we're giving our reason. So when we're formally proving, we have our 5 lines of working in triangle blah blah blah, our evidence, and then our similarity statement with our test. Now our test will be AA or equiangular, okay, in the brackets. So once we've proven, or once we show that two corresponding angles are equal, or two pairs, that those two are equal and these two are equal, that's enough. Because the angle sum of a triangle is 180 degrees. If these two are equal to each other and these two are equal to each other, these two have to be equal to each other, so there's no need to prove or state that the third pair are equal. Just two pairs is enough. The second test is corresponding sides are in the same ratio. So here you can see that 2 divided by 1 is 2, 4 divided by 2 is 2, and 6 divided by 3 is 2. They are all in the same ratio. So when we're talking about our reasoning for our test, I like to use SSS in proportion. We can't just leave SSS side, 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 because that's for congruence. That's saying that all sides are equal, all corresponding sides are equal to each other. But here, for similarity, we have to add these words in proportion because they are in the same ratio. The third one is two pairs of corresponding sides are in the same ratio, and the angle in between those two sides are equal. So it's sort of like SAS, where we've got side, angle, side, and then side, angle, side. The thing is, we can't write SAS because the sides are not equal to each other. The sides are in proportion, they're in the same ratio. So instead of writing all of this out, okay, just write what I have here in brackets. SS in proportion, the two sides are in proportion, and the included angles are equal. When we say included angles, I'm referring to the angle in between those two sides. Those two are the included angles. Okay, and the last test, the hypotenuses and a pair of corresponding sides in a right angle triangle are in the same ratio. So here you can see that the hypotenuse and the second side of a right angle triangle are in the same ratio, they're in proportion. 8 divided by 4 is 2. 6 divided by 3 is 2. So unfortunately, we have to write a lot more than just RHS. Okay. Choose the similarity test that proves that these pairs of triangles are similar. For the purpose of this exercise, we shall call them tests 1, 2, 3, and 4 in the order of the key ideas. So here are our 4. 1, 2, 3, and 4, 1 being equiangular, 2 being SSS in proportion, 3 being SS in proportion and included angles are equal, and 4 being the hypotenuse, and the second side of a right angle triangle is in proportion. Pause the video, have a go with A, B, C, and D. Okay, so question A, you should have said that this is test 1, which is AA. That's equal to that, and this angle is equal to that. That's enough, right? We don't need to talk about this one. What about B? We can see here that this is a right angle triangle, and the hypotenuse over that hypotenuse is 3. This side divided by that side is also 3. So this one has to be test 4. But I would like to practice writing out what I actually need to write out. Unfortunately, in a test, you can't just write 4 or 1. So I'm going to write down hypotenuse and second side of right angle triangle. Right angled triangles are in proportion. Okay, for C, it looks like it's SAS, right? We've got a side, angle, and side, angle, and side. 21 divided by 7 is 3. 18 divided by 6 is also 3. So this one was test 3, I'm pretty sure. And test 3 said side, in proportion, and included angles are equal. This leaves our last one. So I'm going to take the longer side divided by the longer side, that's 3. The shorter side divided by the shorter side, that's also 3. And the middle one divided by the middle one, that's also 3. So that's test number 2. SSS in proportion. Okay, so now that we know the 4 tests, let's have a look at how to actually prove that 2 triangles are similar. So just like proving 2 triangles are congruent, we need 5 lines of working to prove that 2 triangles are similar, except when it's equiangular. Then we only need 4 lines of working, because we just say this pair of angles are equal, this pair of angles are equal, therefore equiangular. Okay, so here we go. In triangle blah blah and triangle blah blah, first piece of evidence, reason if required. Second piece of evidence, reason if required. Third piece of evidence, reason if required. When I say if required, I'm talking about the sides. Okay, so when we're giving a ratio, then we don't need a reason. But if we're talking about angles, we need a reason. Okay, so if angles need a reason. Okay, such as given. If sides, no need for a reason, because we're establishing the ratio. Okay, let's have a look at some examples. Prove that the following pairs of triangles are similar. So I'm going to start off with in triangle ABC and triangle DEF. Okay, make sure that they match. It doesn't necessarily mean that this has to be in alphabetical order. This A is where the 20 degrees is, so I need to start with the D where the 20 degrees is. It's going up here, so I'm just going to follow it. It goes to E, then the short one, which is C, short one, which is F. Okay, so in triangle ABC and triangle DEF, I can see that angle BAC is equal to angle EDF, which is 20 degrees, and that's given to us. Okay, because it's an angle, I need to give a reason. The next thing I need to do is I need to work out, show that the sides are the same ratio. So I'm going to write here, always the longer side over the shorter one. This side corresponds with this. So I've got ED over BA is equal to 3 over 1.5. And 3 divided by 1.5 is just 2. Because it's a side, I don't need to give a reason. The next thing I need to do is show that these two are in the same proportion. So we've got DF over AC is equal to 4 over 2, which is also equal to 2. And so now we can see that they're in the same ratio. Therefore, we can say that triangle ABC is similar to 3 vertical lines to triangle DEF. But we need a test. We can see that that's SAS, but we can't use SAS because that refers to congruence. So I need to write S as in proportion, and included angles are equal. Okay. Question B. So we can see here, right, in question A, that there are 5 lines are working. This is our first line. This is our second line. Here's our third line. Here's our fourth line. Here's our fifth. Alright, let's have a look at question B. In triangle ABC and triangle, now A is the blank one. So I need to start with the blank one here, F. I went to B next, which is 65. So the one with 65 is D. C was last, the 40 degrees. The 40 degrees one is E, so that has to be last. So in triangle ABC and triangle FDE, comma, we can see that angle ABC is equal to angle EDF. Again, the order of these ones don't matter when we're talking about the equal sign, as long as the vertex matches. The vertex here is 65, this has to be 65, and that's given to us. Okay, because it's an angle, we need to write a reason. What else can we see? We can also see that the 40 degrees are equal. So angle ACB is equal to angle DEF, which is 40 degrees. And that's also given. Well, we've established two angles are equal to, 2 pairs of angles are equal to each other. That's enough. Therefore, triangle ABC is similar to triangle FDE AA, or equiangular. So we can see here that there's only 4 lines are working for this. So whenever it's AA or equiangular, we only need 4 lines are working. Every other test requires 5 lines. Okay. Let's have a look at this one. Explain why the 2 triangles are similar. Now when we get a question like this, it just means prove it. Prove that these 2 triangles are similar. So we've got triangle. In triangle, let's do the smaller one, DBC. And triangle, well, we started up here and then we went down and to the right, so I'm going to start up here. EAC. What can we see? We can see that this angle here is common. Angle DCB is equal to angle ECA, Right, always use the letters associated to the actual triangles. So here I said I used DCB because that's part of the smaller triangle, and then I used ECA because they're part of the bigger triangle. I didn't use ECB, right? I went all the way to A. Okay, and that's because that's given to us. Sorry, it's not given actually, it's common. Okay, they share the same angle. What else can we see? Well, we can see that this one here is actually equal to that because of the parallel lines and their corresponding angles. Okay, corresponding angles are equal on parallel lines. So I'm going to say angle DBC is equal to angle EAC. Again, I used EAC, not EAB, because B is not part of the bigger triangle. And I'm going to write here corresponding angles are equal on parallel lines. Okay, I've just done two angles, therefore they have to be similar. I don't need to do the third one. So I can say, therefore, triangle DBC is similar to triangle EAC, equiangular. Alright, now that I've explained that these two triangles are similar, I've proven it, we can actually find the value of x. Now x is this length here, according to this. Because they are similar, we know that the corresponding sides are the same ratio. So that what that means is we actually need to work out what that ratio is. So part B, the scale factor has to be, well, I'm going to find that this one corresponds to this side. So I'm going to take the larger one and divide it by the smaller one, which is 1.5. And now I can say that the larger one divided by the smaller one will equal to 1.5 as well. So x divided by 5 will also equal to 1.5. So therefore x has to be 5 times 1.5, which is 7.5. Okay, let's have a look at solving problems involving similar triangles. If the given pair of triangles are known to be similar, find the value of x. So because we know that they are similar, we don't need to prove it, but we do know that the corresponding angles are equal to each other, and the corresponding sides are the same ratio. Now x is part of a side, so that means it has to be the same ratio. So we can see that whatever x divided by the smaller corresponding side is, x over 3 is going to equal to the same ratio as whatever this one is, 4 divided by 2. So now we can just times it by 3, 12 over 2, which is 6. Okay, so the key is setting this up. Always put the larger one on top. It might not be x. Okay, x might be the smaller one. Always put the larger one on top just to make it easy for yourself. And then if you need to flip it, you can. So let's have a look at C. We know that the sides are the same ratio. This one corresponds to this. So I'm going to put the larger one on top. This one corresponds to this. put the larger one on top. What we can do now is we can just flip them. Because x is in the denominator, I'm just going to flip it, which means I need to flip this one as well. Now I can times by 6, 12 over 3, which is 4. Okay, pause the video, have a go with question D. Alright, so I can see here that the 1.1 is opposite the dot. What's opposite the dot? The 3.3. So they go together, which means that my x, which is opposite the cross, corresponds with the 4.5, which is opposite the cross. So which one's bigger? The 4.5. So I'm going to put the 4.5 on the top over x, which one's bigger? 3.3 over 1.1. I'm going to flip them around. X over 4.5 is equal to 1.1 over 3.3. So x is equal to 4.5 times 1.1. 4.95 over 3.3, which is 1.5. So x is equal to 1.5. Alright, a cone has radius 2 centimeters and height 4 centimeters. The top of the cone is cut horizontally through D. Prove that triangle ADE is similar to triangle ABC. If AD is 1 centimeter, find the radius of DE. Can I get you to pause the video and have a go with this one yourselves? And when you continue playing the video, I'll have the answer right there. Okay, here's my answer. So in triangle ADE and triangle ABC, angle DAE is equal to angle BAC, because that's common up here. Angle ADE is equal to angle ABC, because corresponding angles are equal in parallel lines. And therefore, triangle ADE is similar to triangle ABCEA. Now, whenever you get questions where you've got a triangle inbuilt into another one, usually it's just AA. Most of the time it's AA. Right, question B. If AD is equal to 1 centimeter, find the radius DE. So here I can see that we want to work out what D is equal to, and that's that corresponds with the 2. So I put the big one on top. 2 over DE is equal to, well, we know that this here is 1. So what I'm going to do is I'm going to take the longer side, which is 4, and put it over the shorter side, which is 1. Now that I set it up, I can see that what I need to work out is in the denominator, so I'm going to flip both of them. DE over 2 is equal to 1/4. Multiply both sides by 2. DE is equal to 2 over 4, which is half. Okay, last question for today. Aidan and Jenny come to a river and notice a tree on the opposite bank. Separately, they decide to place rocks indicated with dots on their side of the river to try to calculate the river's width. They then measure the distances between some pairs of rocks as shown. Have both Aidan and Jenny constructed a pair of similar triangles. Give reasons. So what we need to do here is we can see, let's have a look at Aidan's one first. We can see here that they both have a right angle. And we can also see that this angle here is common. it's shared between this triangle as well as the big triangle. So yes, Aiden has. Aiden has constructed similar triangles, and I'll say the reason being AA. Okay, 2 angles. What about Jenny? This one has a right angle, this one has a right angle, but we can also see that this is vertically opposite to that, and vertically opposite angles are equal. So again, she has also done 2 angles. So yes, Jenny has 2, and that's AA as well. Use Jenny's triangles to calculate the width of the river. Okay, so because we know that the 2 triangles are similar, the sides have to be in the same ratio. So question B, we're going to look at Jenny's one, which is the one on the right. We want the width of the river. Let's call that W for width. And this side corresponds to this one. And we know that this 10 corresponds with the 25. So just put the bigger one on top. W is bigger than 8. And 25 is bigger than 10. So we can see here that the width has to equal to 8 times 25, which is 200 divided by 10, that's 20 meters. What about question C, Aiden's triangles? We want to calculate the width. Again, we'll call this W. So this short side corresponds with this long one, and this short side corresponds with this long one. Okay, so let's do always the long one on top. W plus 5 over the short one, which is W, is equal to the long one over the short. Okay, so it seems like we need to use some algebra here. I'm going to cross multiply to get rid of the fractions. So we've got 12 lots of W plus 5 is equal to 15W. I'm going to expand the brackets. 12W plus 60 is equal to 15W. I'm going to subtract 12W from both sides. 60 is equal to 3W. And then I'll divide both sides by 3. The W, or width, is equal to 20 meters. So we get the same answer as question B. However, question D asks, which pair of triangles did you prefer to use? Give reasons. Well, that's up to you, but I personally prefer to use Jenny's. Less algebra is needed. Well, maybe I'll say less complicated algebra. Okay, so whenever you are given questions like this, it's actually always easier to have 2 separate triangles so they're not inbuilt into each other. Whenever it's inbuilt into each other, it makes things a little bit more difficult, but still doable. Alright, so hopefully now you know how to formally prove that 2 triangles are similar. You'll know how to actually associate which tests to use and actually write down the test properly. Don't use SSS, SAS, etc. But you actually need to use SS in proportion or whatever it is. And you know how to solve problems involving similar triangles. Thanks.